Okay, welcome back. We start this second lecture of the day. This will be both practical and theoretical. So please, Jamie, take it away.
Okay, so thank you. What we'll be doing more or less from now is looking at how you put all of these ideas into the computer. Okay. For the people on Zoom, I've put the link to the GitHub repository in the chat. It's also written up here. So what you'll see is that we have the slides from the sessions on the theoretical parts, but then there's also some folders that contain snippets of code. Okay, so there'll be the session 1 code examples, but it's not all of them, but there's a few ones there which sort of show how I got the results that I was showing in the slides. And what I'll be using for now are these two ones here. Okay, so what I want to do is try and give you an introduction on how to do these kinds of operations in TensorFlow, to do these kinds of applications towards PDEs. Now, the big warning before starting, I mean, these programs are not made to do numerical analysis. They're made to do data science. So a lot of the things that we want to do aren't really native functions. And a lot of the arithmetic type stuff is quite straightforward and intuitive and very similar to what you would have in NumPy, for example. But I mean, none of the major data science packages are really designed to do stuff involving PDEs. I mean, I use TensorFlow, other people use PyTorch, other people use Keras. I mean, broadly speaking, they work in similar ways. Obviously, the details are quite different. But what I want to do is show you at least how to do it in this particular package, because this is the one I know best. Okay. So what I'd like to do is start by looking at this Jupyter notebook here, which is arithmetic in TensorFlow, just to show you how these things work. Okay, so TensorFlow is an external package. You have to have it installed and you have to load it just the same way you would NumPy. And everyone always uses TF, so TF is what I'll be using as well. So TensorFlow has within itself, I mean, various data types, which are pretty much all tensors. And it has Boolean types, it has floats, it has all sorts of different things. But I mean, most of the time, the thing that we're interested in are tensors, which are made up of floats. By default, it does everything in float 32. It is supported for float 64, which is what we tend to use more in numerical analysis. This question has come to me from somebody here. Quadruple precision isn't supported. Like as I say, these things are designed around data science approaches where they tend to go for lower precision rather than higher precision, because they want to do things quickly. They don't necessarily want to be very, very precise. So the kind of arrays that you have in TensorFlow, I mean, okay, these have shapes n1, n2, n3. These are very similar to NumPy arrays. I mean, they have to be n1 by n2 by n3 and so on and so forth. You can't have a triangular array, for example. And they come in two flavors, and I'll explain the difference between these two flavors later, which are constants and variables. For some reason, which I fail to understand, if you want to define it to be a constant, it's a lowercase c. If you want it to be a variable, it's an uppercase v. Somebody decided this, I don't know why. So, okay, these guys by default are going to be float 32. If you want it to be 64, you just put comma D type after specifying things. If you want it to be float 16 for whatever reason, well, okay, the same, okay? So we can define a couple of tensors here. So it's very similar to a NumPy array. And now we have these guys. If you want to see what its shape is, you just do dot shape, for example, afterwards, and then it gives you your answers, right? I mean, your standard operations plus multiplying by scalars, etc., etc. I mean, these all work component-wise on your tensors if they're the same shape. Okay, if I have a 2 by 3 tensor and I do plus plus with another one of the same shape, then I get a 2 by 3 tensor corresponding to component-wise addition of all of the different elements. Okay, here I just define two simple 2 by 2 tensors. Then I want to see what happens if I add the two of them together, and okay, we see exactly what we expect, right? Component-wise, we have 1 plus 3 gives us 4, 4 plus 1 gives us 5, and so on and so forth. Yeah. And same for multiplication. All of these things come out component-wise. We can also do, it's in Spanish mode. You can also do squaring, for example. Again, this goes component-wise. We can multiply by a scalar. Again, component-wise. Okay, the sort of standard operations will go component-wise. If you have tensors of different shapes and you try to do things like adding them together, then either there'll be one of two possibilities. It can't work out how to fix the dimensions to make things work correctly, and it just throws up an error. Or it will do what's called broadcasting, where it just kind of repeats one of the tensors enough so that now it's got the right shape where you can do things component-wise. So to see how this works, I mean, here I have a 2 by 2 tensor, here I have a 2 by 1 tensor. I can add them together, and the way that it adds them together is that it broadcasts this x2 to a version with the same shape as x1, which is just made by repeating the entries until it has the right shape. Okay. So if I run these guys, okay, the answer that I get of x1 plus x2, we get this tensor here, which is the same as adding it to the broadcasted version. Okay, this does it automatically. You don't really need to think about it. My advice, nonetheless, is to try and never broadcast because, okay, at least I'm not very good at bookkeeping with making sure that all of the axes are the same. So I tend to do things manually to make sure that I only ever do things with stuff that's the same shape. But I mean, I'm clumsy, so if you're better at the bookkeeping, maybe you can get away with it. And of course, we want to do more than just adding and multiplying. I mean, at the very least, if we have a neural network, we need to apply an activation function. So in all of your favorite functions are in the TensorFlow library. Basically, as a rule of thumb, if it exists in NumPy, then you just change np dot to tf dot math dot, and you get the same function, okay? All of these simple scalar classical calculus functions, again, they act component-wise on your tensors. So I can define a tensor x1 is equal to this 2 by 3 tensor. I apply the exponential function, and I get the component-wise exponential of all of these guys, right? The first guy, this is 1. E to the 1 gives me, well, e. Okay, this is all working more or less as we expected. Same, you have square root. I mean, all your classical trig functions, logarithms, so on and so forth. I mean, they're all there. Two commands that you find yourself using all the time are reduce sum and reduce mean, which do more or less what you would expect them to do. If you put a tensor into reduce sum, then it gives you a scalar output. Okay, this is still a TensorFlow scalar, which has shape nothing effectively, but it just adds up all of the different components inside your tensor and gives you back a number. Okay. Now, if you have a tensor of various dimensions, then maybe you only want to add all of the ones that correspond to a particular axis, right? And then this is straightforward to do. So this matrix, this tensor is 2 by 3. Maybe I just want to sum over the first axis. This is easy enough. Comma, axis equals, and you specify. Okay. If you have a much higher order tensor, then you can put a list of axes in corchete, square brackets. Okay, and then it will do the summation over all of the corresponding ones. So in this case, I do the sum over the first axis. It's a 2 by 3 tensor. So I have the third dimension 3, let's say. And sorry, the other, yeah. So it gives me just a shape 3 tensor corresponding to the sums of the other guys, okay? And of course, when we're doing things like integration, when we're doing PDEs, we're going to be using these types of commands all the time because we're going to be adding up things together. And obviously there's reduce mean as well, which is exactly the same functionality, except now it divides by how many things you have in your list. Okay, again, works on axes, or you can do a reduce mean over the entirety of your tensor. So a lot of this, I mean, this is basically the same as NumPy for the most part. So, okay, what can we do with TensorFlow that you can't really do with NumPy? I mean, the most fundamental operation is taking derivatives. Okay, when we do a gradient descent, even if we're not thinking about doing anything involving PDEs, we need to take the gradient. Now we could sit there for 100 hours trying to manually write what the gradient should look like depending on our 1,000 parameters, or we can use automatic differentiation. Okay? And automatic differentiation is incredibly easy in TensorFlow. Basically, if you can write the function, it can give you the derivative. Okay? So the way that this works, and there's two types of autodiff. I mean, I'm just going to treat this like a black box for the sake of this course, because you don't really need to know how it's working under the bonnet. The only thing that you should really keep in mind is that there's two types of automatic differentiation, which is forward mode and backwards mode. For 99.9% of the cases that you're interested in, you'll want to use backwards mode. And forward mode exists. The way that it's implemented is a bit different. Really, forward mode is when you have a very high dimensional output. Now, if we are trying to find the gradient of a loss function, our output is one-dimensional. Right? So we want to be using backwards mode because it's efficient when you have a high dimensional input and a low dimensional output. Forward mode is the other way around, which sometimes you might want to use, but I mean, these cases are much rarer, okay? So how do we do backward mode differentiation in TensorFlow? I mean, it's really, really straightforward. So I just define some tensor. So this is going to be the input of the function that I'm interested in. Just say x2 is some, well, order 3 vector. Now, the first thing I need to do is to define a gradient tape, okay? This guy you can call whatever you want. I normally call it T1, T2, T3, depending on what job it's doing. But always starting with TF dot gradient tape. Again, these guys go with capital letters. And everything that you do goes in here, okay? So you want to do all of the calculations that produce the thing you want to differentiate in this indented region, okay? Now, if you have a constant, you need to tell it to watch the constant, right? I want to take the derivative with respect to x1 at the end. And because x1 is a constant, I need to tell the gradient tape to watch what it's doing. And this is all how it works within the backpropagation process that gives us the derivative, okay? So I tell it to watch x2, which is really saying at some point I want to take the derivative with respect to x2. I do whatever calculation I want with x2 after this point. So in this case, I'm just going to do the simplest thing possible. I have 3 numbers. I add their squares together. Right? So I evaluate this. This just gives me a number, which would be what, like 4 plus 16 plus 36. Then outside of this indented environment, I just say dy, this is going to be my gradient, is equal to T1, which corresponds to this guy. Gradient y, the thing I'm differentiating, x2, the variable with which I'm differentiating. Okay, so really, really simple. Then obviously this one we can do by hand. We know that the derivative of sum of xi squared is going to give us 2x in each component of the gradient. And we see it's doing what it should, right? 2 goes to 4, 4 goes to 8, 6 goes to 12. Okay. So, and this way of taking derivatives is really, really simple. This is the same way that you can take derivatives of your loss function with respect to your trainable parameters. You essentially just evaluate the loss in the middle of this indented environment, and then at the end you say gradient with respect to parameters. When you're evaluating your loss function itself, which also depends on derivatives of the neural network, you basically do the same thing. You just evaluate your neural network at a bunch of points, take the derivative with a gradient tape, and then use that to define your loss itself. Okay? So it makes it really straightforward, and you don't have to think too much about what's going on. If you don't put this watch command in here, then you end up with a problem. Okay, this is because this is a constant, and it doesn't watch constants by default. So if I repeat basically the same calculation, but now I don't tell it to watch, then my dy, which gets printed, is none. Okay, so this is just one thing to always have in mind when you're doing these calculations. The same is not true for variables. Okay, this is one of the big differences between variables and constants. variables are always watched by default. Okay, so if I do the same thing as I did before with the constant, so this would have given me a none if x2 were a constant, it automatically watches it because it's a variable inside any gradient tape. So, I mean, this can be good and this can be bad. If you don't actually want the derivative with respect to the variable, then this introduces some cost, which doesn't really give you any benefit. But this can also be useful just to save time when you're coding and avoid issues. Again, as we have here, okay, now because it's a variable, we have no watch, and it produces the gradient exactly what we should expect it to be. Okay. Questions or doubts up to now? Okay. So, then. Um, so when we're doing these kinds of applications, I mean, we're not just interested in taking derivatives of scalar functions. Right? And if we want to do the derivative of our neural network at all of our integration points, then what we have is for every x, we have a value of our neural network, and we want to take the correct derivative of each u at each data point with respect to their x. Okay, and maybe you want to do things that are higher dimensional as well. So various ways in which this gradient tape environment works is that if you have your output and your input are of the same shape, then it automatically works component-wise. Okay. So in this case, we still have this same x2, which is just a tensor of 3 dimensions. Now, if I do this command, now my y is going to be another tensor of 3 dimensions. Okay. Now, if I take the gradient of y, which is a 3-dimensional vector essentially, with respect to x, it takes the derivative of this component with respect to the first component of x, this component with respect to the second component of x, and so on and so forth. Okay? So obviously, this is very useful if we're doing quadrature to evaluate a loss function involving a neural network, right? And if we think of a simple scalar problem in 1 dimension, for each data point, we have a u. We want to take the derivative of that bit of my output with respect to the correct input, and then we get the list, which is all of the derivatives at our data points, as well as the list of our neural network at all of these data points. So again, we can double check that this is going correct. Again, what we have is that each of these components in y is just the corresponding component in x squared. So we should be getting 2x in each of these cases. What was our x? 2, 4, 6. Here we get 4, 8, 5. So of course, sometimes you want to take derivatives of derivatives. Right? If we have a second order PDE, then we need to be able to evaluate second order derivatives. Again, this is quite straightforward. Remember, basically anything that we calculate within the gradient tape environment, we can take the derivative of at the end. So we can do this by putting a gradient tape inside a gradient tape. Okay, so we find the first derivative, and then we take the derivative of the second derivative, same way we do it by hand, right? So we can see how to do it in this particular case. So here, what I want to calculate is the Hessian matrix. Okay, so we're really going to see 2 different things at the same time. The first thing that we're going to see is how to do a second derivative using this kind of language. Well, okay, you just put the gradient tape inside the gradient tape. This is straightforward. Then the other command, which is here, is Jacobian. Okay, well, the Jacobian command does what you would expect the Jacobian command to do. Okay, if I have a vectorial input and a vectorial output, then it gives me a tensor, which corresponds to the Jacobian of this. Okay, so it takes all of the derivatives of all of the components together. Yep. Oh, so Okay, so in this case, I mean, okay, the fact that the answer is the same is like more of a coincidence than anything else because of the structure, right? So in this case, okay, if I change this line, what we see, Spanish. So in this case, my y, because I've done reduce sum, my y is a scalar. Okay, in this case, my y is a vector. Okay. Yeah, yeah. Yeah, so I mean, if I change this function to something else, then okay, I could make these derivatives at the end different. It's just because essentially, I mean, in this problem, everything's decoupled. Right? And it's a sum of things that only depend on the particular component. Okay? So what we can do, okay, we'll make a little change here as well to make everything clear. So what I have is my y in this case, because I have a reduced sum. This gives me some scalar output. Then I take its gradient. This is going to give me a vectorial output. And now I take the Jacobian of this vector with respect to its input, or the Jacobian of the gradient gives us the Hessian. And everything should be coming out the way we expected, right? Okay, so we have y, which is our scalar output, dy, which is our gradient, and then our Hessian, as expected, is a 2 by 2 matrix. Okay, and then all of this, I'm doing really simple functions here, but you can do the most complicated things if it's all in the TensorFlow language, using all these classical calculus functions, whatever, then it's going to do this derivative just as easily. Okay, you never have to do anything by hand when doing derivatives in TensorFlow. So, okay, as well, if we have a problem where we have a tensorial input and a scalar output, okay, then we end up with basically the same kind of thing as we have when we have a vectorial input. I mean, sorry, this is the one. This is vector. I knew that I was saying nonsense. Okay. So in this case, what we have is a tensorial input, and then this goes into a vectorial output, but somehow these things are still sort of aligned. We can understand this as being component-wise, right? So we can think of each of these as being some vector that goes component-wise into a scalar output somehow, right? So we can think of 1, 2 gets mapped into 1 squared plus 4 squared, which gives us 5. Then the next one is 3 squared plus 4 squared, which gives us 25, and so on and so forth. Again, the gradient command just works basically component-wise if you sort of respect the dimensions of everything that you have in here. The more complicated case is if you have something vectorial going to something vectorial. Right? But still, I mean, the commands aren't that complicated. And what we're having is we're thinking, so we have n, which is the number of tensorial or vectorial inputs that go into our function. We're doing them in kind of batch procedure. Then they get outputted into a shape which is now n2. So again, we have n component-wise outputs where each output is 2-dimensional. Well, then if we do the Jacobian component-wise, then this should give us something which is n number of components, 3, 2, right? And again, batch Jacobian precisely respects this kind of structure. Okay, so what I have is precisely this kind of thing here. I have a bunch of 3-dimensional outputs. Okay, I do slicing to give me the first, second, and third component. I can stick my 2 scalar outputs together to give me a component-wise vectorial output using the stack command. And then batch Jacobian gives us the answer in precisely the kind of shape we would expect, right? So this tensor here, this is my output. We think of 4 as being 4 point values that I'm sticking in, each being a 2-dimensional vector. Then I take my derivative, sorry, my Jacobian component-wise. So I have 4 Jacobians corresponding each to a 2 by 3 matrix. Okay? And all of this here is quite simple to use with the black box, as long as you're paying attention to the dimensions of the inputs and the outputs. Are there questions or doubts up to this point? The hardest thing when doing this is bookkeeping to make sure that all of your axes are in the right place in that experience. which is why I always test things with prime numbers in terms of the number of inputs, because I mean, it just can't work if it's working that up. Now, one of the really big features in TensorFlow is that there's two types of functions with TensorFlow objects. And the default is what they call eager execution, which is basically regular line-by-line execution. You give it some function, it goes, okay, I calculate this, and now I calculate this, and so on and so forth. Okay? Really, this is just a regular Python function. So what I have here is I have some eager function, which is just a standard function. And what I'm going to do is just evaluate sine of x squared. Now, the other type of function that lives within TensorFlow is graph mode functions, or graph execution. So this only works if you have TensorFlow inputs and TensorFlow outputs. And all you have to do to tell it to do it in graph mode is put this little guy before, like that, at tf.function. Now, what this does, again, we can just think of this as completely black box, but TensorFlow is based on graphs which represent the flow of information from tensors to each other. And essentially, at least as far as we're concerned, all this is a very optimized version of our function. So if I define, this is exactly the same function, the only difference is I've put at tf function before. What's going to happen when I put a vector inside? Well, the first time I call this function, it's going to build this graph. Okay? This has a cost, but it's there. And then it's going to give me the output. But now the second time that I run this function, what it's going to do is instead of doing a line-by-line execution, it will go to this graph, which is the optimized version, and it'll be much quicker. Okay? So what we can see, I'll just quickly run this. So I have my eager function and my graph function. These are exactly the same function. The only difference is that, well, same function in terms of inputs, outputs. The only difference is that one is going to work in graph mode and the other one's going to work in. Okay? So for each, I'm going to evaluate them on some rather large random vectors. So I have some randomly chosen x. So this is how you would do a sample of 10 to the 8 random uniform numbers between 0 and 1. And what I'm going to do is evaluate my eager function on this giant vector, measure the time, do the same with my graph function twice, and see how long it takes. Oh, sorry, 3 times, and see how long it takes. So when I do my eager execution, okay, it takes 0.69 seconds. When I do the first pass on the graph mode, it's 0.14 seconds, but then on the second and the third, it's gone down by a third. Okay? It's kind of strange. I think it's because this is just such a simple problem. And normally creating the graph, which is what adds this extra 0.1 second, this can be quite an intensive procedure. If you're using the black box functionality of TensorFlow and you press, okay, optimize me this, there's normally a very noticeable pause before it starts doing anything. And that's when it's making the graph. And this can be quite an expensive process. In this case, because it's such a simple problem, okay, it ends up being cheaper than an even mode execution. Okay? But we can see here very, very clearly that, okay, we have to pay a little bit more the first time that we do it, but then afterwards, okay, here we have 0.05, here we have 0.7. So this is incredibly useful if we want to do iterative methods, because if we're doing an iterative method, we basically have the same function, we just put a different input in. We don't even change the shape of the input, okay? But by default, if you do a TensorFlow function, if I were to change this to a different shape, it would have to redo the graph. But there's ways around this. But if we're putting in exactly the same shape, size, whatever of data in every single iteration, just with different values, we can get huge speeds up in time, which makes it very, very useful if we want to do 20,000 iterations of training a neural net. Okay. Okay. So there's some issues for arithmetic type stuff. There's never any problem. What graph mode does have a few problems with are uses of things like conditionals, iterating over tensors. I mean, it can't do basically, because then, I mean, it thinks of it as a symbolic tensor when it tries to do the graph, and it doesn't let you do it. So it doesn't have a fixed value yet. So, I mean, for arithmetic type stuff, you can always do it, but you have to be, I mean, really it's ifs, fors, whiles, things like that you need to be careful with. But I mean, a lot of the time, if you're doing sort of operations with big tensors, if you can do it with a for, then thinking about it a bit, you can only do it without a for as well. Okay. One thing that I want to add here, I mean, if you're using the kind of black box functionality of TensorFlow to do some optimization, which is what we'll see in a little second, you don't need to think about putting things in graph mode. If you do all the black box functionality, then TensorFlow puts everything into graph mode automatically, and you don't need to think about it. If you're doing something a little bit more personalized, then this is something you should make sure you're doing before every single command that you're calling over and over again, because it's not there by default. So this document, and this was all about, the basic arithmetic of this important thing on functions, how we evaluate derivatives, and how we do basic arithmetic with tensors. And the next thing that I want to talk about is how to do some very basic things with neural networks in the TensorFlow language. Okay. Now, what I'm going to show here, and the thing that I want to repeat again is that TensorFlow is designed for data science problems. So okay, if we want to do things involving PDEs, we have to rip open the black box a little bit. If we're doing very, very simple problems, then we can do less ripping open of the black box. Okay, so if we just want to say minimize the L2 norm of u prime prime minus f, then it's not too difficult to make changes in order to do the kind of things that we want. Okay. So in this one as well, why is it letting? Because I didn't get about my people, sorry. This one. Okay, so before getting into how we do this with PDEs, we're just going to think of some really simple interpolation problems, which is what this software is really designed to do. Because if we want to hack it to make it work what we want to do, we should know how it works when it's doing what it should be doing. Okay. So in this basic NN file, okay, all we're going to do is some really simple interpolation problem. I have some noisy synthetic data, and we're going to train a neural network to do an interpolation problem. Nothing complicated at all. So I'm going to specify some data length in, especially when we're talking about doing things like Monte Carlo integration. We need to know how to do random sampling. So the way that I make my data, I show you how to do the main sampling methods. If we want to do a uniform sample, then you just say, okay, I want my sample to have this particular shape. In this case, my tensor is going to be 500 by 1. Its minimum value will be -1. Its max value will be 1. Okay. Then my y data is going to be my x data cubed. So I have, this is somehow my true function. And I'm going to add a little bit of normally distributed noise with mean 0, standard deviation 0.0. Okay. So I'm going to take a little data here. Now, going back to our very, very first bit of the course, the first thing that we need to do is decide on an architecture. Now, it's very simple to make a simple neural network in TensorFlow, and everything is built up on layers, and it has a whole bunch of layers inside its black box that we can use without having to think too much about it. So there is an even simpler way of doing this, but I'll be doing it in this way because this is more flexible for the kind of things that we want to be doing. Why do I have this written twice? There we go. So what is this code doing? Okay, first I have to say what is my input to my neural network? Okay, my input is going to be basically a bunch of scalar objects, and it's going to act point-wise, component-wise on these scalar objects. So I specify my input with tf.keras.input with whatever shape my input is going to be. Then all I do is I just take all of my layers, defining their inputs, which are going to be other objects of this form. I get my output, which is the guy on the left, and then I keep on going until I get to whatever I want. So the simplest layer, which is the one which is almost exclusively used at the level of PDE type approaches. I mean, this is a dense layer. So what is the dense layer? What this is saying is that we map our input into R20 according to an affine map where the matrix and vector are trainable parameters. Then we apply an activation function, which I specify myself. If I don't specify one, it means there isn't one, or it's the identity equivalently. A lot of the common activations you can put as strings, like ReLU, hyperbolic tan, sigmoid, you can put them as the name. But you can put any function that you like here, just writing it as a regular TensorFlow function. Right? If I want a sine activation function, then I just do tf sine. Right? But I mean, the classic ones, you put as strings. But I could also put tf.nm.relu, which is how you call a ReLU function. That's it. Okay? So I've specified how my inputs go to my outputs being expressed as the inputs of layers. And then I just say, well, my model is going to be tf.keras.model. My inputs is this guy. My outputs is this guy. And now I have my neural network. Okay? And you can put as many layers as you want here. You can do all kinds of crazy things, but let's just keep it really simple for now. So I run this guy and I use model.summary just to make this little table which appears here. Okay, so it summarizes, this is what my inputs are, what's its shape, how many trainable parameters sit inside it. The same for the dense layer in the middle, and the same for the dense layer which gives me that output. And this can just be useful to have an overview of what your neural network looks like. It tells you how many trainable parameters. Right? Done something strange, you might end up with thousands of thousands there, and that gives you a hint, oh, maybe I should do this. So once I have my neural network, now effectively it just works like a function. I can put in inputs and it gives me outputs. So what I'm going to take here, so I have my X data, and I'm just going to take the first 10 components of it, because I have 500, just so it doesn't print a bunch. I put my X data into my neural network, and I get my output. Okay, again, component-wise as it appears here. Now, to train my neural network, what I need is a loss function and an optimizer. Right? These are the sort of second and third steps in this overarching way of doing things. Now, if we want to do some very, very simple classical data science-y type approach, then this is really straightforward. Okay, so you have to specify your loss. In this case, you can really specify all kinds of functions here, but I won't dwell on this. If you want to do the mean squared error, i.e. we have the inputs, we apply the neural network, take out the output from the data, square and sum. Right, this is mean squared error. I say my loss is MSE. Then my optimizer, which I have to specify as well. Again, I'm using the black box functionality. I don't need to tell it how to do the updates and whatever. TensorFlow has a whole bunch of optimizers which are in the black box that we can just quote. All of them are of the form tf.keras.optimizers. And then whatever afterwards. Okay? If I want to change this to SGD, then I put SGD. If I want to change it to SGD with momentum, then I do SGD with momentum equals 0.5. Right? Okay, you don't have to go into a lot of detail with this. Then once I have my architecture, which is in my model is defined, I have my loss function I want to minimize, I have my optimizer, then I just compile my model like this, model.compile. Optimizer is whatever I said my optimizer is. Loss is whatever I said my loss is. And now everything is basically ready to do my training. Okay. Now, there's more things that you can put in here. If you want to put other metrics, if you want to put certain other things, they can go into here, but we're just thinking of the simplest way to do things for the moment. Then once we have our model compiled, then fit is how you do the training loop itself. So there's all kinds of different variations on how you can organize your data. The simplest way, if we're doing some kind of interpolation problem, is I say, okay, I have my X data, these are my inputs, my Y data, these are my outputs, so X equals X data, Y equals Y data. I want to take 10% of my data to use for validation. I'm not going to train over it. Okay, one line of code, I say validation split equals 0.1. How many epochs? So an epoch is when you go over the entirety of your training data. And a batch, so what you do is you divide your data. Okay, I have 500 data points. I use 50 for validation. I have 450. So what I'm going to do in this case, by having batch size 10, I divide this into 45 groups, and I iterate over 10, I iterate over another 10, and I keep on going until I'm done with the data, and that counts as one epoch, which now I do 10 times. Yeah. Just want to make the comment, all this stuff on batch sizes isn't really that relevant when we're talking about problems involving solving PDEs, but it's good to know that this functionality exists. So this will take a little second, but I tell it to run, and it gives me all of this information whilst it's training. Okay, so each line corresponds to an epoch. It's going too quickly to see that this line is advancing, but if they were bigger, you would see this line advancing as it's training, and tells you, okay, how long this corresponds to each batch. It tells you the loss that it's calculated at the end of the epoch, the loss on the validation set at the end of the epoch. See all of these metrics live, essentially. Now, what we can do just to see if we've got a reasonable approximation, well, in this case, we do. Okay, so these blue data points, these correspond to the data that I fed into my neural network. This black line corresponds to the solution after doing the training, and okay, have a decent training, right? Okay, this is good. Now, one thing that I put in the very first line, here. So in this history, so I said history is equal to model.fit. Okay, why did I say history is equal to my training? So when we're training, it's creating these metrics, but it also saves them. Right? So by having history equals, and I have to do this anything that I like, what this allows me to do is look at my metrics or whatever it is that I'm measuring during training. You can tell it to measure all kinds of things. And now I have access to that information afterwards if I want to see how it was behaving. And this can be done. This should be the next guy. Yeah. So, okay. This history is because I called it history. I could call it whatever I want. Information. Okay. So these are all represented as classes. So the history bit of this class. This is what saves all of our metrics. And this is a dictionary kind of structure. Well, the name of the loss corresponding to each iteration is loss. The name of the validation loss is val loss. These guys are recorded automatically. Okay? If you don't use a validation set, then obviously val loss doesn't exist. But if you use a validation set, it automatically saves all of this information, and then you can access it later. So with this information, so now loss list is just going to be classical NumPy list. Each entry corresponds to one iteration. Each entry is a float. Basically the same for the validation loss. And we can see how this guy is going. Both of them are going down, and they're more or less in agreement, which tells us that there's not really any major overfitting. Oh, see, this is a very, very simple problem. I needed 10 iterations. So if you have a more interesting problem, then this might give you a lot more information than what we're seeing here. Within these kinds of training loops, I mean, there's all kinds of different things that you can stick into this to make it have other functionality. One of the big ones is our metrics, which, I mean, the validation loss is a metric. Right? Any other loss that you can think of, you can tell in the training loop, okay, watch this metric. Then you get another list of numbers at the end of how it's measured, how this thing is evolving. Okay, it doesn't enter into the training itself, It just measures it and gives you the number to have a look at afterwards and do whatever you want with it. The more functional ones are callbacks. All right. Callbacks, there's a load of them. If I open up the callbacks documentation, I mean, there's various ones here, which all have different types of functions, but as well, you can define your own custom callbacks. And if you go into the documentation, it explains how to do a callback yourself. But these are useful if you want to do some kind of functionality within your training loop that goes beyond measuring a number or the optimization itself. Okay? So, for example, if you want to reduce your learning rate when your validation loss isn't improving, that would go into a callback. That's a default one that sits inside it. You can define callbacks to do all kinds of strange things. But basically, anything that you want to do, which involves measuring what's happening in your system and making some change based on it, this would have to be programmed into a callback because this is somehow the only bit you can touch when you're using this kind of black box functionality of TensorFlow. So just to show you how they work or how you implement them at the very least, and the one that I'll use is called early stopping. So early stopping, it has something that it monitors. You can choose any metric which is inside your problem. I'll take the validation loss because that's the obvious one to choose here. And what this does, okay, there's all kinds of other settings which I've left as their default. But what this is saying is, if my validation loss is no longer improving, i.e. it goes up, stop training and restore the best weights where the best weights corresponds to the ones with the lowest validation loss, right? I mean, it's an agreement with the metric that you have there. So if you're doing some kind of very noisy, sparse data, whatever interpolation problem, then you would expect after a certain amount of time, you're going to get overfitting, and this is when your validation loss goes up. And that's when you should stop training because that means you have a problem. When these three lines of code, they do that for you, right? I mean, they say, okay, the second this thing starts going up, game over, we stop training, and we put the best weights that we found according to the validation loss into our neural network. So I define a list. This list I'm calling callbacks because I wanted to. You can call it anything you like. Inside it, I put all of the callbacks that I want to include. If I wanted to include more, I could put comma, TF callbacks, any other one, any custom one as well. Then with this, now the only change that I have to make is that when I'm doing my model.fit, I just include callbacks equals callbacks, and all of the callbacks in this list will be put into my training loop so that so that it does what you expect it to do. Now, another thing worth bearing in mind, my model has already been trained. I'm already very close to a reasonable solution, at least that's what we saw in the picture. So this doesn't go back to the start. This is the same model as before. It's somehow initialized at a very good solution. So we don't expect it to improve much. And what we can see, it goes through the training loop. Now my validation loss at the end of the first epoch, it's 0.0042. At the end of the second epoch, it's gone down a little bit. Third epoch, it goes up by 0.0001. So it says, game over, we're going to stop training. And it remembers the weights that corresponded to the end of this epoch and puts them back into the neural network. Right? You can imagine if there was some horrific instability, maybe here the validation loss would be 10 to the 5. Right? You don't want to remember those weights. You want to remember the good ones that you had before. This one does it for you. Okay. And I think, I mean, that's more or less all I wanted to say on the more black box functionality. I mean, are there any questions or comments on this part? Then, just for the last, we finish at 1:30, right? Okay. So just to finish things off, I mean, I'll only do a little segment of this document, which I don't think I can put it up on the GitHub yet, which is just some comments on how we can try and implement some of these ideas when we're doing things involving neural networks, PDEs. So then going back to this three-step process, we have the architecture, we have the loss, and then we have the optimization scheme. I mean, in our architecture, one of the things that we said is that it can be very, very helpful to manually put the boundary conditions into our neural network. Okay? If we know that we're trying to solve Poisson's equation with homogeneous Dirichlet conditions on some domain, we have two choices. We can either add some penalization into our loss function to tell it to satisfy the boundary condition, which mathematically speaking is kind of ill-posed, or we can just multiply the output of our neural network by something which is 0 on the boundary and positive on the interior. Now we know that our neural network satisfies the boundary condition, and we can forget about that part and just think about the PDE. So to do this, what we need to do is change the architecture of our neural network in the TensorFlow language. And the way that we do this is by defining a custom layer. Okay. So remember what we had. If when we were defining the neural network in the completely black box sense, I mean, we have these dense layers, so activation function applied to an affine function with some trainable parameters. We just used all of the standard ones here, but we can define a layer to be basically anything we want. We can give it any input, do any calculations in the middle, and make it give us any output that interests us. So how does this work? I mean, these work as kind of class environments. So because I want to make a layer, which I apply at the end of my neural network, which just basically multiplies it by something that's 0 on the boundary, I create this class, I give it the name that I want. I'm going to call it BC layer for obvious reasons. Now this somehow inherits from the layer, the Keras layers class. So you put brackets tf.keras.layers.layer. Now, in this case, I'm going to allow my layer to depend on certain parameters. I'm thinking of a 1D problem, and I want my function to be 0 at A and B, but maybe I want to change A and B. So I'm going to allow A and B to be parameters of the layer, much like in a dense layer. We can choose the number of neurons in the activation function as parameters in the layer. Right? We specify them once, and then they're fixed. So we do the initialization, self, A, B. These are going to be my endpoints. We do all of these steps here for the initialization, and then load them into the class. This is more or less the same as any other class would work. Then we define how the layer takes the inputs to the outputs. So this always comes in the call command. Okay, so when you define a layer, it's the call part or the call function that tells you how the inputs go to the outputs. So self, as always, as we're working with a class. And now in this case, so I have my inputs. This is what's going to go into the layer. And we think of this as the neural network without the cutoff function. Now I can do basically any operations I want here. So I'm going to have my inputs is the input of the previous layer and my x. I need to know x to be able to evaluate the cutoff function. And okay, this step is just to reshape because I want it to be an n vector or n by 1 vector, and n by 1 vectors are the default TensorFlow. Then I just define this guy, which is equal to 0 on the boundary, positive in the interior, and use the einsum command, which is similar from NumPy. Are you familiar with this one? Yep, just to stick the output of my neural network together with my cutoff function. Now, once I have this defined, I can use this like any other layer in the TensorFlow environment. There's a question. I think this one I haven't uploaded yet because I don't think we'll get here today, but it will be available. So just to show you very quickly that this actually works and how it works. So I import all of the guys I want to input. I define this guy. Now, the way that I define my neural network is now basically the same as the way that I defined it before. Okay, what I have now is a fully connected feed-forward network. The only difference is that at the end, I multiply it by essentially x1 minus x or something like that to make it 0 on the boundary. So my early layers, so I have input, then I apply it through a dense layer, then I put this guy through another dense layer, then this guy through another dense layer. Okay. This time we have a deeper network, but it's all the same commands. Now I define my output to be my BC layer, which I defined before. -1 and 1, these are my points where I want my function to be 0, which go into the layer. And remember that the inputs of the layer were the output of the previous layer and the x values, which I need to know to evaluate the cutoff function. Okay, but really the way that you put this in once you've defined the layer is the same as all of the default ones. So, guys, run hiding from this guy. And what we can see is that if I now evaluate my neural network just on some uniformly spaced points, which I make from here, now what I have is precisely what I wanted. In my neural network, whatever the values of my parameters are, I'm always going to be satisfying this Dirichlet condition that I wanted in order to have to not worry about it when I get into the optimization. Now, just for the last little bit, to show you how ridiculously flexible layers are, one of the big complications is TensorFlow works great if you want to do something like a mean squared error loss. The losses that we're interested in, these involve derivatives of the neural network, and this isn't built into the native functionality. So somehow we need to define a loss function which involves derivatives of the neural network itself. And for this, we can't really use the native functionality as such. But one of the simplest ways, if we're doing simple problems, is to use layers to define our loss function. So what's the idea? I have my neural network, which represents my solution, right? This is a Keras model, and I define it, and I have it there. Now I make another Keras model, which isn't actually a neural network. All it does is it has inside it my neural network, and its output is the loss itself. Okay. As far as we're concerned, this is really just a function which is defined inside the TensorFlow language. As far as TensorFlow is concerned, this is a neural network, or at least a neural network model. Okay. So I can do basically the same idea. I define loss layer. I load into this layer my neural network, which is my solution. Okay. This now exists inside my loss layer. And now within my call, okay, my inputs, I don't actually do anything with them. Okay, these are like dummy inputs or phantom inputs. I take a Monte Carlo sample using, okay, this is between -1 and 1 of integration points. Now with my neural network, which lives inside this layer as well, I can evaluate its second derivative doing all of these same autodiff gradient techniques. I find my residual, which is the second derivative minus whatever my right-hand side is. I square everything and take the mean. Okay, this is essentially my integration, right? So with my loss layer, which doesn't really have an input, but its output is the loss itself, I can define another model. Okay, this isn't really a neural network, but TensorFlow doesn't have it. We know that, but TensorFlow doesn't. So I define it in exactly the same way as I would define a regular neural network. I have my loss layer, which takes as an argument the U model when it's establishing the class. It has this fake input that doesn't actually do anything, and the output is the loss itself. And again, I have this neural network, and what you'll see, there were no trainable variables explicitly in my loss layer. But when I do my summary, it says there's 2,700. That's because all of the trainable variables in my real neural network, my solution, are inherited automatically. So if I do a training of my loss model, it also updates the trainable parameters in my U model, which is what I actually want to update. Okay? This is very hacky because it's not designed to do this, but I mean, it works. So that's nice. So once I have my loss model defined, again, I can just put in my dummy input, which doesn't actually do anything. It doesn't change the output at all. And now I get a number which corresponds to my loss function that I'm interested in. Now, when we're doing minimization over a TensorFlow model in the TensorFlow language, we have to specify a loss function at the mean squared error before. But now the loss function is the output of the network itself. So how do we kind of fix these two issues? Well, it's simple. We define a custom loss as far as TensorFlow is concerned, which just outputs. Okay, so if you have an interpolation problem, the typical loss functions in TensorFlow have y true, which is your y data point, y pred, which is the output of the neural network. So MSE, which would be a function of this form, is just y pred minus y true squared. In this case, y pred, which is the output of our neural network, is precisely our loss. So we just say the output is y pred. Okay. Very happy. But with this, now we can do everything basically in the usual TensorFlow black box. Okay. We have a loss model, we compile it with some optimizer. These guys don't really do anything, but you have to specify them. They have to be the same dimensions as well. I can say how many epochs, I can use callbacks, I can do all of the black box functionality using basically the minimal changes by sticking everything into a layer for my loss. And now I can train it. And I say, did you notice that little pause before it started? This is this process of making the graph. And this is what takes a long time on the first step. But when you have something more complicated, then it goes much, much, much quicker afterwards. This is going to take a little while to train. That's why I've only put it for 250 iterations. And it's not going to be a very good solution because you should normally be leaving these things for thousands. Right? But once we have it, we have all of this information coming out here. And here we have my approximate solution and my exact solution. Okay, this has been a very, very short short training loop. So we don't expect a particularly good solution, but we see, okay, it's a good first attempt for not very much work, right? And again, part of the other benefits of this is that once you do it in the kind of TensorFlow black box kit, again, you have access to all of these metrics that it's saving during training. Okay, so if I want to see how the loss was evolving, one button again. Yeah, so now we can see how this thing is evolving. So in this kind of approach, I mean, it works nicely for very, very simple problems because everything is very straightforward, essentially. You're taking advantage of as much as you can of the TensorFlow functionality, but it's also kind of limited at the same time. You can use all of this kind of idea. For example, if I know my exact solution and I want to see how the H1 error is evolving over time, then I have to put another layer which measures the H1 error, and then I have to define some metric to capture all of these things, and it becomes a little bit more complicated. But then once you get into things that are more advanced, like, for example, this least squares optimizer that I was mentioning in the previous session, then it becomes almost impossible to do in this language. So what I'll be talking about in the next sessions is sort of a much more flexible framework that can definitely do all of these kinds of things, but I find it to be much more useful if you want to do more advanced things or things that don't really fit nicely into the black box. I think that's everything I wanted to say for today. Please ask if there's questions or anything like that. I'll say when I'm defining this, so when I do the loss layer and it contains the parameters of the actual neural network. I mean, so And one of the things which is kind of it's a good thing when it's good and it's a bad thing when it's bad. If you have any variable which is inside your Keras model, any variable at all, when it's training, it will optimize over. Okay? You can't, I think there's a way of telling it not to, but sometimes it works and sometimes it doesn't. Okay? And for example, what I could do is put here self.lambda equals tf variable, whatever, 1. Now, if I put something involving lambda here in the training loop, it will automatically optimize over it as well. So any variable that exists inside your model will automatically be optimized over in the optimization training. Now, this is good if you want it to be optimized over, and it's bad if you don't.